not much participation is there in today's meet. So anyway, today actually we need to have a few issues. So let me just point it out. The first thing is that I think before our Puja vacation, we have started boundary layer flow, and I think we reached up to, we had a discussion up to momentum integral equation, or one common momentum integral equation. So we need to finish the remaining part of boundary layer. Remaining part of boundary layer flow, and we had also calculated the problem sheet on potential flow. So I need to have the follow-up, I mean status from you regarding this problem sheet. Okay. Status of practice problems on potential flow, right? And there is another important issue, that is the pass test, CT. Okay. So we need to finalize the date duration of exam syllabus. And mode, I think the mode, of course, is still now online. Okay, so that needs no discussion. So we will fix this up towards the end of our meeting today. So regarding the boundary layer flow, I mean, if you have gone through the materials already provided to you, the video notes and also the written notes. I mean, so it was actually the momentum integral equation, and then some approximated velocity profiles if you take up for flow or flat plate, and considering no pressure gradient, that means that dpdx term, if it is set to equals to 0, and your momentum integral equation reduces to a single term, where actually the momentum thickness is involved. Okay. So that, I mean, then if you proceed for solving that equation to get actually this delta, that is the boundary layer thickness, and then towards finding out, I mean, the purpose of this exercise is basically to find out the wall shear stress tau W, and thereby we can get the estimate of the shear force acting on the surface over which flow is occurring. So, in order to get that, these are the different ways by which, for a more realistic flow, we can get the shear stress at the wall.
স্যার বলছিলাম যে ওই মানে ডি ইউ নট ডি মানে ডেল ইউ নট ডেল এক্স ওই টার্মটা মানে এক্সিস্ট করছে কি করে? কারণ কি মানে ইউ নটটা তো আমরা অ্যাজ একটা প্যারামিটার টাইপের না, মানে প্রতিটা সিচুয়েশনের জন্য ডিফারেন্ট, তো ওই টার্মটা এক্সিস্ট করছে কি করে এখানে? মানে এক্স এর রেসপেক্টে দুটো চেঞ্জ করবে না ওই মোমেন্টাম ইন্টিগ্রাল ওইটাতে?
হ্যাঁ, you are talking about this du not dx, right? That is what you are asking.
Yes sir, yes sir. হ্যাঁ স্যার।
So what is the problem? U not may be constant, U not may not be constant. If U not is a variable in the direction of x, if it is having a gradient, then the U not dx will be there, isn't it?
মানে গ্রেডিয়েন্টটা থাকবে কি করে? মানে ইউনটটা তো আমার ফ্রি স্টিম ভেলোসিটি একদম মানে এন্ট্রান্সে, তো ওটা তো চেঞ্জ করার কথা না। যদি গ্রেডিয়েন্ট থাকে তার মানে গ্রেডিয়েন্টটা আসছে কি করে? কারণ কি আমি তো ওই মানে ওই জায়গাটাতে তো আমি আপনার আইডিয়াল ধরে করছি আর কি, ইমপ্লিসিট ফ্লো ধরে।
I mean, this term actually is actually U not dx. If you look back, this is actually the pressure gradient written in terms of U naught. All right.
Yes sir. হ্যাঁ।
So, if you do not have a pressure gradient, that means if your pressure is not changing in the direction of x, that means your U naught is also not changing in the direction of x. Thereby, the U naught dx is equals to 0. However, it is not the case for all type of flow situation. Typically, the flow.
না ওটা ইউ নট লেখা হচ্ছে কেন? মানে ওটা তাহলে আমি নর্মাল মানে জেনারেল একটা এক্স এর মানে এক্স এর ফাংশন হিসেবে ভেলোসিটি লিখবো, আমি ইউ নটটা কেন লিখবো? ইউ নটটা তো মানে ইকুয়েশনটা যেটা দিয়ে করছে সেটা তো পি প্লাস হাফ রো রো ইউ নট স্কোয়ার ইকুয়ালস টু কনস্ট্যান্ট ওটা দিয়ে করছে, তো ওইটা তো মানে আমার একদম
U naught is the velocity outside boundary layer. Okay. So typically,
Yes, sir.
we, I mean, starting to maintain consistency, rather, I can say, in potential flow also, we have the designation of uniform flow as U naught, right? So that is the free stream velocity. Typically, it is maintained in the perspective of boundary layer flow as the velocity outside the boundary layer, which is U naught. So that is the free stream velocity if there is no boundary nearby. Okay, so that doesn't mean this U naught will remain constant. It will remain constant if you are having a flat plate over which flow is occurring. But instead of a flat plate, or in other words, if you are having, say, closed conduit, for example, a pipe, through which flow is occurring. So the pipe may be a straight pipe with no change in its diameter. It could be a pipe of changing diameter. It's a kind of a tapered cross section. I mean, like that if it is a converging section. So there, you see, your U naught, or in other words, the velocity at the center, which we can say as the maximum velocity. So that maximum velocity may not remain constant at different cross section due to this convergence, or the other way if it is a diverging section. But we can say that center line velocity is out of the effect of boundary layer. In the same analogy, for a flat plate, if it is a straight and parallel plate, I mean, or you can say if it is not changing its gradient, the plate orientation, so we can say that U naught is not changing. So here actually u naught does not mean always it will remain constant. It is basically the velocity where your effect of boundary layer is minimal. That means when your after delta, basically the velocity or when y is approaching delta, uh, your small u is nearly equals to u naught. Small u is the variable here within the boundary layer. Okay, so beyond boundary layer, you are having velocity u naught, which may change, may not change. বোঝা গেছে? My
আচ্ছা,
point is
ক্লিয়ার স্যার।
that, yes. So what we were talking actually, so with this boundary layer, this momentum integral equation gives us a tool, and or in other words, an approximate method. It's an approximate method to find out this boundary layer thickness, followed by the shear stress, the wall shear stress, which will give us this shear force. That is what we call as skin friction drag in the later part. And so we have started with a very simple profile. Basically, why this is an approximate solution, because here you need to assume the velocity profile. Okay, so that velocity profile may be just a linear profile like this, or it could be, in general, it could be nth order polynomial like this. It is written here. So to start with, we had a linear profile, which is denoted as a naught plus a1 y by delta, where y by delta is actually eta. So then you need to impose the boundary conditions, and then you have to find out this delta star, that is the displacement thickness and the momentum thickness. So once you have the velocity profile, you can replace it with u by u naught term, and this is basically a routine integration. I think I need not go through that details. In the video lecture, it is already there. So the methodology is something like that. So once you first you need to have a profile starting from linear profile to more higher order profiles, and then you need to evaluate delta star and delta m. Although if you are considering a zero pressure gradient, your delta star, that is displacement thickness, may not be required to find out this tau w, because u naught d u naught dx will be equals to 0 for zero pressure gradient. But this momentum thickness will be required, and that actually, as you see, that leads us to finding out this delta in terms of x. So you get this relation delta by x with respect to the Reynolds number, which is also eventually function of x. So that actually gives us a relation from momentum integral equation, and thereby you can write down by recalling Newton's law of viscosity, from where you can write the wall shear stress tau w as equals to mu the pressure gradient normal to the direction of velocity, that is here is u naught by delta. The delta is being replaced from equation 11 actually. So from here you get the expression of delta, which gives you the expression of tau w in terms of x. So these also you can, if you, for a length small l, if you now integrate over the length 0 to L, you get the force acting on unit depth, you can say. If it is a plate, so one dimension is L and the other dimension is considered to be 1, so that you get this friction force per unit depth, you can say. So then there is a definition of coefficient that is known as mean skin friction coefficient, which is nothing but this friction force over half rho u naught square into L. Again, actually here is there into 1 unit depth. Then the local skin friction coefficient is another term which is actually without this L, which is denoted as local skin friction coefficient. For linear profile, actually, then it is basically the F you can able to find out for different profile, and accordingly the expression of this coefficient gets changed. Now, then the exercise has been extended for a quadratic profile, and one can observe the changes actually that took place in the expression of delta star, delta M, and tau W. So ultimately, when you come to the towards the end, actually this delta by x, one can observe there is a change. Earlier it was for linear profile, delta by x was square root of 12 Rex, I think. Yeah. So this is basically the delta by x for linear profile. This is square root of 12. Here it comes to be 5 over square root of Rex. So the denominator remains same. It is basically the numerator which gets changed for different velocity profiles. If you go for cubic profile, it would be something around 5.134, something like that, if one can do that exercise. And actually, there is another technique by which one can have an exact solution of the boundary layer. That is basically this delta by x. This is a solution, right? Because we are interested to have the knowledge of the development of this boundary layer, which is characterized by the thickness, boundary layer thickness delta, which is a function of x. So you need to have an expression of this delta in terms of x, and of course other parameters characterizing the flow. So here it is number, which is also a function of x. So we have another methodology, which actually is an exact solution, which gives an exact solution for flow over a flat plate. But that is beyond the purview of our syllabus. So that leads to a solution which is known as Blasius solution. And here in the approximated solution, if you increase this velocity profile from linear to more higher order, it gradually one can observe it comes more close to the exact solution. That is, from quadratic, if you do the exercise for cubic, you can compare. So that is one part of our momentum application of the momentum integral equation. And then we extended the same exercise for turbulent flow, because this momentum integral equation can also be applied for turbulent boundary layer. Here also we consider zero pressure gradient. But one interesting aspect of this particular study is that here in the boundary layer, in the turbulent boundary layer, we have used an analogous method. Means basically comparing with a situation of flow where you have some kind of experimental findings available, and actually that is being compared in some way with another situation, that is flow over flat plate, because we have started the situation of our boundary layer considering flow over flat plate. So the laminar boundary layer part we did. For turbulent boundary layer, it is basically being compared with flow through pipe. Basically, you can see, as I have already stated while clarifying this U0, that for a flow through pipe, if you recall the development of the flow, basically they are also, there is a change in the velocity profile, and ultimately when the flow is fully developed, we have a parabolic kind of a velocity profile, meaning at the center or at the axis actually, we have the maximum velocity designated by UC. So this is, we can say, analogous with this U0 for a velocity, which is just beyond the boundary layer thickness delta. Okay, so these two are analogous, you can say, where in case of pipe, you of course, you are having the boundary of the pipe, where due to no slip condition, it will be zero velocity, and velocity will gradually increase and it will reach to the maximum, because after that again it will actually being going to be affected by the boundary on the other side. So it's a radial direction. If you get the cross section, it will be like this, whatever schematic is shown here. Okay, so what is the experimental findings which we actually we have used here? Any idea? Have you gone through it? Anybody? My question is that what is the experimental finding on flow through pipes, which already you have learned in your fluid mechanics 1. So using that relation, which is valid for turbulent flow, typically, not the turbulent boundary layer, because the concept of boundary layer was absent in our fluid mechanics 1, but the finding where we understood the loss due to flow, that is the friction, major loss, the friction loss, and the related equation, which is experimental. That particular finding is being used here for flow through pipes, and thereby which is transferred to flow over a flat plate. Basically, I think you can recall the Darcy's equation. Okay, what is the basis of Darcy's equation? Can anybody try to answer? What is the basis of Darcy's equation or Darcy-Weisbach equation?
The frictional loss or pressure drop in relation, মানে frictional loss relation mainly.
Yeah, that's true. But my question is, what is the basis? I mean, if I ask you what is the basis of Hagen-Poiseuille equation, where from it came? Or what is the basis of Bernoulli's equation? I think one can...
Bernoulli to energy conservation.
Right. So it's basically from the conservation principle, considering certain situation, I mean, certain constant or some assumptions. By applying certain assumptions, you reach to a equation called Bernoulli's equation, which is a special form of energy equation. So the basis of Bernoulli's equation is energy conservation. Likewise, if I ask you what is the basis of Darcy's equations, is there any conservation principle involved, or is there any theoretical principle involved from which one can able to derive
conservation of mass?
Conservation of mass. How we can say that? Darcy's equation, where is mass there? Anybody else?
the conservation of flow?
What is conservation of flow? It's basically, as you have said, I mean, it is a relation between, actually, your Darcy's equation is the relation between the head loss due to friction with several parameters. One of them is velocity, square of the velocity. Then you have length of the pipe, then you have diameter of the pipe. So HF is equal to FL by D V square by 2G. That is the Darcy's equation, isn't it? So, and where this F is the friction factor. So this Darcy's equation, if you, I mean, nobody actually has remembered, the basis of this Darcy's equation is purely experimental. I mean, several experimentations were conducted to see the effect of different parameters on the head loss. One of them was this length. So for same diameter pipe, different length chosen, and the pressure drop across that length was measured, and same flow actually was used to flow through the pipe. Okay, so that your V, that is the average velocity, remains same, and if your cross section is same, that is the same flow. So by changing different length, it was observed that the head loss also gets changed, and it is linearly proportional with the length. So if you increase the length, your frictional loss gets changed. I mean, it also increases. So HF is proportional with L. In a similar manner, it was found that this HF is inversely proportional with the diameter of the pipe, and it is proportional with the square of the velocity. These are the observations, experimental observations, and based on that, actually, those observations are being clubbed to a single form of equation by introducing a constant, proportionality constant, which is denoted as friction factor F. So that one can write HF is equal to F L by D V square by 2G. Okay, so this 2G, I mean, that is basically to give this particular equation a shape, where the V square by 2G is in terms of head, isn't it? Right?
Yes, sir. Yes, sir.
Okay, so that is the basis of Darcy's equation. So which is applicable. This equation is applicable for flow through pipe. It is not, obtained directly for cases of flow over flat plate. Okay, so that is why at the beginning, I mean, this experimental information about turbulent flow in pipes can be used in the study of turbulent boundary layer on flat plate. Okay, this is one. By similarity, actually, the basis of this study is similarity principle. Means similarity principle for which particular area, that is wall. Because at the wall for pipe, you are having for no slip condition, velocity 0. At the, for flow over a flat plate as well, it is the same. Velocity should be equals to 0 for no slip condition. Okay, so that is one very important basis of this analysis, which then for turbulent flow, actually, we know that instead of having a linear relationship for either pipe flow or flat plate, the relationship for turbulent flow follows the power law expression. That is basically U for pipe, U by UC is equal to Y by capital R to the power 1 by N. and that is for flat plate. In y by r is being replaced by y by delta, and u naught is replaced by uc is replaced by u naught here. So these are the two changes that one can observe. Okay. So this index n varies from 5 to 8 depending on Reynolds number, and in this study actually we set the value of n as 7 for typical value of Reynolds number 10 to the power 5. Okay, then actually it is the same consideration of a elementary volume, control volume, for a steady, fully developed flow situation of pipe. As you can see on your screen, this elemental volume, the left hand side the pressure is P, and the right hand side we have a pressure drop delta P that gives us the pressure to be P minus delta P, and apart from that, on the surface we are having the wall shear stress tau W acting. So there, as this is steady flow, the net force should be equals to 0. So there should not be any acceleration term. So that leads to this particular form of an equation, or in other words, you get the expression of tau W, in which you can write delta P in terms of rho g HF. So these HF actually, which we just now discussed, can be written in terms of Darcy's equation form. There's F L by D, U average square by 2G. Okay. So that leads us to the expression of the wall shear stress in terms of friction factor F and the average velocity, along with the density. Okay, further, another experimental relation between the friction factor and Reynolds number. Like, for example, if you once again you can recall, for laminar flow through pipe, we have F equals to 64 by RE. That actually is not an experimental finding. Rather, if you combine Hagen-Poiseuille equation with Darcy's equation, you can analytically find out this relation of friction factor with Reynolds number, isn't it? If you can recall. In your fluid mechanics 1, I think that you have studied. However, for turbulent flow, you have to resort on some experimental finding, and one of that is this one, which is known as the Blazier's equation, which gives us the relation of friction factor with Reynolds number, and it is Reynolds number RE to the power minus 1 by 4. Okay. So these F can now be replaced using Blazier's equation. So here in this exercise, we have the two experimental findings. One is the Darcy's equation, the other is the Blazier's equation. So that we are applying for flow through pipes till now. And then with some, by expanding this Reynolds number in terms of kinematic viscosity, average velocity, and the diameter, that is twice R, and with some manipulation, we can get the equation 18, which relates the wall shear stress with a ratio of velocity, that is U average, and UC, that is the center velocity, or the velocity at the axis of the pipe, and nu by R to the power 1 by 4. So then what we did, we actually tried to find out this U average and UC by applying the definition of this flow, that is pi R square U average, or if you have a strip and then if you want to integrate, knowing the velocity at that particular strip of dr thickness. So that is another way you can integrate over the entire cross section, ranging from R equals to 0 to r equals to capital R. And by that, actually, we can have the definition of U average by equating these two. So that, I mean, here, actually, the first change that has been taking place, I mean, from the radial component, I mean, the radial parameter, this R, is being replaced by the dimension Y. Again, I refer to the very first figure where one can understand. I mean, this is the Y direction, which is at any boundary, you can have the perpendicular direction, that is Y, in a pipe, and in case of a flat plate, this Y will be always same. But this Y is having a relation with the radius variable smaller and the radius of the pipe. So R can always be written as capital R minus Y, isn't it? Basically here, you can see that R, the smaller I'm talking about, starts from R equals to 0 at the center, isn't it? And it will be maximum at the boundary, which is boundary means solid boundary I'm talking about, which is the radius of the pipe. In case of flow or a flat plate, the variable small y starts from 0 at y equals to 0, right, which is at the solid boundary. And then it becomes maximum at a particular x, that is delta, which is the boundary thickness. So here the approach is opposite, isn't it? So that should be kept in mind. So coming back to this particular, So this actually leads to the change in the limit as well. One can observe. I think this is very straightforward, and you are well aware of this kind of exercise. So by doing some series of these changes and reorientation, so as this is a definite integration, or you can, if you can do it properly, it gives you this twice UC 49 by 120. That is the value of U average, which ultimately gives us the ratio U average by UC, which actually we are looking for. So here, I mean, in this equation 18, and this is the ratio that we need to find out for flow through pipe. So this ratio is 0.8, and then if you substitute it, and you get this expression of tau W in terms of the center line velocity UC, which is analogous with U naught, okay, for flow or a flat plate. And in the next stage, actually, we tried to replace the UC with U naught and R, capital R, with delta. Okay, so these are the two replacement which is being done from the similarity, right? And then by, again, the power law relation for flow or flat plate, and that is U by U naught as equals to Y by delta to the power 1 by 7. This we have used to find out this momentum thickness. As you know that momentum thickness will be required when you are going to use the momentum integral equation for zero pressure gradient, right? So that you get the expression of tau W in terms of delta. So typically for that particular velocity profile, you get this tau W, and the other way from which you have the value of tau W is from that analogy with flow through pipe and flat plate, and those are being equated here. This is the form of the equation. Now, this part actually you obtain by that analogy, and this is from momentum integral equation. Okay, so this you obtain from MIE, and this is from analogy with flow through pipes. Right, so now we are having an equation where d delta dx is equal to 0.2314, then nu over u not delta, so another delta is there, which again by rearranging, ultimately you get this final form of delta x as you have done for linear profile or quadratic profile in the previous two previous cases. Okay, so the difference here is you are here handling a turbulent boundary layer over flat plate, and you are actually using this tau W expression. Instead of using your Newton's law of viscosity, which is basically applicable for laminar flow or parallel flow. So that is basically the problem here for turbulent flow. So that is why we need to resort on some other situation, but similar one. So that leads to this expression of delta by x, and then the rest are not being done here. If one can extend this to find out tau W and thereby the skin friction coefficient. Okay. Then definition of friction velocity is being written here. I mean, that is typically to define the viscous sublayer. If you can recall the development of boundary layer, starting from laminar to turbulent, I mean, in between transition, and in the turbulent boundary layer within itself, there is a viscous sublayer. So in order to define this viscous sublayer, again, some characteristic velocity that is known as friction velocity, which is being defined in terms of wall shear stress. So these forms analytical part of boundary layer flow in order to find out the shear stress on wall. So one may ask why we are interested to find out this shear stress on the wall, because the answer is let me have some idea from you first. Why we are going to find out this wall shear stress on the, for this boundary layer flow. What is the purpose? What may be the purpose?
Slowing down.
Slowing down for
drag calculation.
স্যার ডিজাইন পারপাস কতটা ট্রেস হবে
Aerodynamic design drag কমানো.
What is drag?
So slowing down.
What slowing down?
So slowing down by the wall shear stress. Sir.
কতটা পাওয়ার লাগবে আমার
The
ওটাকে
friction due to the air called drag.
ইয়ে করে হিসাব
Yes. কতটা পাওয়ার লাগবে কি বললে?
স্যার দেবজিৎ স্যার
কতটা পাওয়ার লাগবে? Actually, this wall shear stress, as you have seen, that it will basically responsible for the force, that is the tangential force due to this wall shear stress, which will act opposite to the motion. That means the very characteristics of this particular force will be to oppose the motion. That means it will actually a detrimental situation for any object which is flowing, which is moving through a medium of fluid, be it water or any other liquid or air. So and this is basically a surface phenomena. That means this particular force will act on the surface which is exposed on the fluid. Now the thing is that if you want to move the vehicle through this medium, you need to overcome this particular opposing force. So always we need to do that, and when you want to overcome this, you have to exert certain amount of additional energy. So that means you need some energy or power to overcome this. If you do not have the power to overcome, you cannot able to move, right? So your movement or motion will be slowed down. So that is what is basically the characteristics of friction, and which always calls for some amount of power. So one thing is that you need to estimate. One need to estimate how much amount of power is required to overcome friction, because that should be provided to the vehicle. And the second part is the which is more and more relevant as we are going through a very difficult situation of power crisis. I mean, crisis in terms of price. I mean, it's so you need to go on designing the object, which could be a car, which could be a air-going vessel or sea-going vessel, whatever, so that you can minimize this requirement of power, which will be consumed to overcome this opposing force. Okay, so one is the estimate of the requirement, how much power is will be required to overcome this. And the next one is you need to do something to minimize this power, because this we consider to be loss, because this power you cannot recover. Friction is a phenomena which is irreversible. Okay, so I mean that means you cannot recover this energy which you will consume to overcome that. So that is the main objective. By having the knowledge of boundary layer flow, one can able to find out these, or one can able to estimate, rather we can say, and the amount of this friction, which is also known as the skin friction. This is absolutely due to the formation of boundary layer, and that will be acting on any surface which moves through a fluid. Okay. In the next part, we move on to a flow over curved surface, where actually the pressure gradient cannot be ignored, or where the pressure gradient exists. Okay, so you can see the effect of pressure gradient and boundary layer separation is the subtopic here. So in the first case, flow over flat surface, we have neglected this dp dx term, or in other words, u naught du naught dx term. Here actually, as we are having a curved surface, due to that curved surface actually, you can have a situation where the boundary layer, or in other words, the flow may not be able to attach itself with the boundary throughout its passage over the curved surface. Okay, so that is typically what we call as boundary layer separation. That means the flow may separate itself from the solid boundary. And how it happens, a schematic on your screen you can see. Here, I mean, you can also relate that this U naught, as at the beginning of this particular discussion, somebody has raised this U naught issue. If you look into this particular schematic at particular point A, the typical velocity profile is being drawn, where we have du dy. That means it is a curved surface, but at any point you can have the direction normal to the surface, which is y, and tangential direction can be thought of as x. Okay, so at each and every point you can have this coordinate frame to be attached. So in the tangential direction, the flow velocity is u as a variable, and just after the boundary, it is denoted as u naught, which incidentally here gets changed, as you can observe, from point A towards point C through B. At point C, you can see that the u naught, which is maximum, that is u naught max. Okay, so here your u naught gets changed. Typically, I mean, this is the case. You can why actually u naught is changing, because it is a situation of a converging passage. We can say if this boundary was not there, you may have flow in this direction. I mean, in this direction only. So due to this particular presence of this boundary, the curved surface, the flow is trying to adjust itself. So in this process, the passage through which the flow is now being permitted is gradually decreasing. The cross section of the passage I'm talking about, right? Otherwise, if this boundary was not there, you will be having a constant cross section through which flow is occurring. Due to this, you are having, it is just a linear version of this curved surface. You are having this particular boundary now. So that means instead of having a cross section of this much area, now at any point, say this is my A, you are having a cross section of this much, right? So what does it mean by your continuity principle? You are having the same amount of flow rate, as it is a steady flow situation we are considering. So what will be the velocity at my cross section at the station A here in this figure? Will it be less than u naught or greater than u naught? What do you say?
Greater হবে sir.
Greater হবে. কেন কবে greater? Because আমার cross section টা reduce করছে. The cross section is being reduced. Okay. So to maintain the same flow, u naught or whatever you denote it should be increased, right? And then we are actually here. I am just showing you the another analogy that is beyond the boundary layer. What is being shown here, edge of boundary layer. Beyond that, the situation will happen like that. Okay, and beyond that boundary layer, if the velocity gets decreased or increased, eventually here it is being increased, as we have correctly said. So if it is being increased now from your Bernoulli's equation, we can prove that pressure will gets decreased, isn't it, at this cross section A?
Yes, the pressure will be decreasing. So
Pressure will be decreasing because your velocity is increasing to maintain same energy level, which should be beyond the boundary layer. Your energy balance sheet will follow the Bernoulli's principle. So it is just basically the trade-off between the velocity and the pressure. If your velocity gets decreased, your pressure will increase, and vice versa. If the velocity gets increased in the direction of flow, your pressure will decrease. So typically this situation, And we have seen that at the very beginning of boundary layer flow discussion, that this change of pressure can be extended within the boundary layer as well. So keeping that in mind, if you now look into this situation, you can see that one can see that in this from point A to point B, your this del u del y remains positive actually, okay, and then the value of this del u del y gets decreased, okay, because of your decrease in pressure, okay, so that you are going to have a situation where your del u del y at y equals to 0 gets equals to 0. So that is typically the representation shown here at point D. Okay, so this is the point. That indicates that beyond this point, I mean, okay, before that, at point C, what happens? You have reached to the maximum value of U naught, where, in other words, we can say we have attained the minimum pressure condition. Just below this particular schematic of velocity profile, we can observe the plot of pressure in the direction. Okay, so that is, I am highlighting this one. This is basically the plot of pressure had it been ideal flow. Okay, so at point C, which corresponds to maximum velocity U naught max, here we are having the minimum pressure denoted as P min. Okay, so then actually due to this curvature, we are having increase in the cross section of the divergent part beyond point C. So up to point C, we are having in the direction of flow decrease in pressure. That means one can say dP dx or del P del x is less than 0 from point A to point C. That is what is called negative pressure gradient, right? Which is favorable. Because why it is favorable? Because it actually helps to attach the flow with the solid boundary. Okay, from point C onwards, as you are having divergence, means you are having decrease in velocity. I think nobody will disagree,
Yes, sir.
right?
No, sir, disagree করবো না।
Okay, so it will be a decrease in velocity now, followed by increase in pressure. Or in other words, you are having del P del x greater than 0 or positive from point C onwards. That means in the direction of flow now, as you go onwards, you are experiencing more amount of pressure. That indicates that flow is being resisted, isn't it? That is the physical situation.
Yes.
Flow is going to be resisted, right? So due to that, it is actually decelerating the flow. And if this effect goes on, that means this opposing effect due to pressure increase goes on, there could be a situation where instead of having a forward direction or the direction of flow, which is here left to right, you may have a flow in a reverse direction. That is typically what happens here at point E. This is the representative situation where you can have a reverse flow causing what we call as AD. Okay, so typically this situation of AD has been started from point C onwards, the moment from where you are having a positive pressure gradient, which is known as, or which is called as adverse pressure gradient. It is not favorable because it ultimately leads to shift of the boundary layer, which otherwise remain attached with the body or with the solid boundary. So this is a representative point where we can say that del u del y becomes equals to 0, and then it could be negative. So this negative del u del y indicates the reversal of velocity. Okay, so this is the point from where your effective boundary layer gets shifted, or actually it is being lifted above the solid surface. Okay, so this line actually is the edge of boundary layer. That is basically our delta y delta line. Okay, so the moment this separation occurs and followed by this formation of the reverse flow, so here you are having a direction of flow like this, just at the bottom like this. So that calls for a kind of circulation or a disturbance in the flow path, which is known as eddy formation, and this zone actually will cause multiple number of eddies, and this entire zone is known as wake region or disturbed region of flow, where flow is being separated from the boundary layer. Because we know that because of no slip condition, your flow velocity will be 0 at the boundary. That is also a reason the flow always tries to attach itself with the boundary. But if it is a curved surface due to change in pressure, this kind of a situation may occur, and the moment it happens actually, from that point onwards, the pressure will remain more or less same. Because of this eddy formation, it actually is a turbulent situation. So even if you are having a laminar flow over this curved surface, after separation, boundary layer separation, the situation will be turbulent, and you can have an average pressure condition beyond that, which is typically shown here by this line. It is the actual condition. So effectively, what we have, if we consider the entire surface starting from A to E, the pressure condition, if you can now observe it at the beginning, you will be having a stagnation point where the pressure will be maximum, and in the direction of flow it goes on decreasing to P mean, and then it starts recovery. And the moment you are having a boundary layer separation, instead of recovering, it will remain at that particular value, more or less. Okay, so in the context of the entire body now, what we can see that at the rear end of the body, we are having a pressure which is less than the pressure at the beginning or at the frontal side of the body. Now you can compare this with the situation that we already dealt in case of our potential flow for a cylinder. So instead of any arbitrary curved surface, if you are having now the same, if you recall the same cylinder that you study in your potential flow, where we have seen that the pressure variation was absolutely symmetric, resulting no thrust or force due to this flow acting on the body. Okay. So this was the CP variation or CP plot with respect to theta, or one portion, one hub actually, 0 to 180 degree as it is shown. It will be repeated for the next hub. Okay. So actual for ideal case, it was a complete recovery because the pressure falls to, the pressure coefficient actually, CP falls to -3, indicating this PC becomes equals to negative at 90 degree theta, followed by its recovery phase where it starts rising, and then it attains 1 at 180 degree and then again it will be repeated like that. So thereby the pressure distribution over the cylinder will be absolutely symmetric, which results no resultant thrust or force acting on the body due to the flow. So that is why it was a paradox, D'Alembert's paradox. I mean, no net force acting on a body which is subjected to a flow situation. But the moment you are having this boundary layer concept, this is what actually happened, where you have the pressure recovery incomplete, resulting this amount of deficit in the pressure. So what is the effect? What is the effect due to this deficit? The effect is another type of force that will be acting on the body now. Had it been full recovery, there won't be any kind of net force acting on the body. Because of this deficit in the recovery of pressure, we are having another type of drag force, which is known as normal pressure drag or form drag. Okay, that is due to the boundary layer separation and formation of wake. So it is because of this formation of wake after the point of separation, you are having a pressure which will remain as it is at the very starting point of separation, and it is definitely not that pressure at the frontal side, or you can say it is not that pressure as the pressure at the beginning of the body surface. So due to this boundary layer flow, we can have two different types of drag force. One is known as skin friction drag, that is typically the one for which you require this moment of integral equation or some exact methodology to find out. That is known as the skin friction drag due to the wall shear stress tau W. And the other one just now we have discussed, it is basically the drag due to the pressure difference at the two difference between the two halves, frontal and rear end. Okay, so it is also written here, I think, as well, in a more or less same manner. Yeah, poor pressure recovery and so on. So I'm not going into that. So these two different types of drags, they are having two different reasons. Okay, and as we have understood that we need to reduce this drag force, whatever be the nature of this drag, be it form drag or skin friction drag, ultimately you need to reduce, because both of them are of same nature. In a sense, I mean, both of them are the opposite nature. That means they are opposing the motion. Okay, isn't it? Both of them are opposing in nature, so you need to reduce. So again, here, I mean, in order to reduce the skin friction drag, the technique is one type, and in case of reducing the form drag, the technique is different. For reducing the skin friction drag, actually, you need to have a very polished surface so that the wall shear stress will be minimized. However, for minimizing the, another technique is that if you reduce the contact with the flow of the body, or the contact area is minimum, then also you can able to reduce the skin friction drag, because it is ultimately force that is equal to shear stress at the wall tau W times the surface area in contact, that is A. So any one of the two terms, if you can reduce, effectively your force will be reduced. So either you can reduce tau W or you can reduce this A. So A, if you want to reduce, that means minimal contact with the flow or with the fluid. Okay, so for reducing the drag due to form, I mean that is the second one, that is the pressure drag. One thing is that as we have, if we have understood that the reason behind this form drag is boundary layer separation, so we can say that if we can delay the boundary layer separation, that means, or in other words, if we can shift the separation points more and more towards the rear end, typically like this, where you can see that the wake region is being minimized, that is being achieved by having a particular form or shape of the body denoted as streamlined body. So in case of a cylinder, typically, as you can see just below figure, the wake region is more, or the separation point is more towards the top point. Okay. So more and more this point comes in this direction, we will be having more and more wake region and less pressure recovery. That is the extreme one, which is here, which we call as the bluff body. Here, you are having a minimal contact of fluid with the surface. That is this small bevel-edged portion. However, here you are having this point as the boundary layer separation point as well. So the entire rear half, that is this entire region, is wake region. So there will be maximum form drag, minimum skin friction drag for this type of a body cross section. Okay, now of course you need to make a optimization between these two different types of drag force so that you can have the best effect, right? So definitely, if you go for this type of a blob body, the form drag will be dominating, and it will be. You need to see whether it is more than this type of a body. Okay, so this is.
স্যার একটা কোশ্চেন আছে
বলো।
স্যার বলছি এগুলো কি সবই মানে এক্সপেরিমেন্টালি ডিটারমাইন্ড নাকি এগুলোর কোনো মানে ফিজিক্যাল কারণ আছে যেটা কোনো লজিক্যাল কারণ আছে?
Skin friction drag, as we have seen, skin friction drag is more of analytical. Whether you are following moment integral equation or the Lecture's equation, so it is analytical. And this phenomena of boundary layer separation is from the concept of boundary layer flow, which is also analytically established. Okay, with, of course, with experimental proof. Okay, so I do not
এটা অ্যানালিটিক্যালি এলো কোথা থেকে, মানে কোন একটা সলিউশন কি এইরকম দেয়, মানে এই যে ওয়েক রিজিয়নটা যেমন আমরা পাচ্ছি, বা ধরুন ওই যে বাউন্ডারি লেয়ার যে ওই একটা শেপটা যে হচ্ছে একটা বাউন্ডারি লেয়ারের, তো ওই জিনিসগুলো কি কোনো ইকুয়েশনের সলিউশন নাকি ওগুলো অন্য কিছু?
না, অফকোর্স প্রাইমারিলি এটা এক্সপেরিমেন্টাল ফাইন্ডিং থেকে এসছে, ঠিক আছে। অ্যাপ্রক্সিমেটলি এক্সপেরিমেন্টাল যে ফাইন্ডিংটা, ইউ নিড টু, if you are looking for a exact equation from which if you just have a plot you can get like that, I think that is for a particular case only. In general, if you want to have a solution of this boundary layer, you have to resort on numerical means. I'm talking about some kind of CFD solution. Using software, actually, you can have the prediction of this boundary layer possible. Okay, but it is not by because whatever we are doing up till now is a 2D planar situation, but a real flow situation is 3D. So you need to have a 3D model developed and then go for the solution, which I think can be done by CFD technique. You can go up to a particular level. Typically, for the laminar flow situation, you can definitely, I think, by using either linear or quadratic or even cubic profile. By considering that, you can able to draw, you can able to plot this formation of boundary layer with the boundary conditions well defined. But of course, for turbulent region, it is not that straightforward. That I can say. All right. But
So for boundary layer, then we have to do some statistical averaging.
If it is turbulent, of course, you need some kind of statistical averaging. If it is laminar,
Laminar would be an easy case.
not easy case. Analytically, you can try, but for turbulent situation, as you can see, for turbulent situation up to a certain level, we had an analytical solution. This one, this equation 21. This is for a flat plate, turbulent flow or a flat plate. But again, and this is only for the skin friction part. Okay, if you want to estimate the amount of drag due to this boundary layer separation, of course there is technique, there is technique, analytical technique that exists, but again that is beyond the scope of our syllabus. Okay, so as probably I have already mentioned at the beginning that boundary layer flow is a comparatively new topic in fluid mechanics in comparison to the other like potential flow or compressible flow. So still this particular area is evolving. It is just at the 20th century, this concept of boundary layer coined by Prandtl. So comparatively it's a new one, and it requires numerical means to solve the flow situation and to predict the drag force. However, by experiment, actually, if you are having a turbulent flow region, the averaging is more, prominent, because turbulent means it's mixing, and more mixing is there. Your averaging will be more accurate. Okay, that is the advantage of turbulent situation in comparison to laminar situation. So, if you are able to measure the pressure difference across the body, that means if you consider the front point and the rear point, there if you have some pressure probe, and if you can able to measure the pressure drop delta P, so by that directly you can able to find out the drag. That is this one. CD half rho U naught square into A. This is another way where basically by experiment one can able to find out the CD for different flow situation. Now, if you can able to measure the terminal velocity of the velocity which is constant, that means at steady state velocity, that is also denoted as terminal velocity. And if you know the frontal area of the body, you can find out this total drag force. So without going into these theoretical details, by resorting on this drag coefficient, which depends on the shape of the body, not the size, then Reynolds number, and it is dimensionless. So some experiment if you can do, and these are actually being available in handbook, the variation of CD for different separate body. Okay. So in fluid mechanics, this is very important. For different shape, if you have the variation of CD with Reynolds number, for example, for a sphere, the variation is available for different Reynolds number, the variation of CD. Now, if you are having a sphere of the size 10 millimeter diameter and another sphere of 1 meter diameter, I mean, the variation of CD remains same. Okay. So, using that, if you can able to find out only the terminal velocity, you can find out the steady state drag. Of course, not the transient. I mean, there is another subject altogether, another topic altogether to evaluate at the transient what is the behavior of drag. But for the steady state, as far as steady state is concerned, you can, by the knowledge of this drag coefficient, you can find out the total drag. That actually includes the skin friction also. Okay. So this is just the, I mean, initiation, I can say. More detailed study is required to get the knowledge in a complete manner, or to go for any kind of advancement in this particular area. All right. So that is there. I mean, is it clear to you? You think that actually you are looking for whether it is completely experimental or it is by analytical means one can have. Both are there. You require, I mean, here you need to have some kind of experimental findings, and then you need to develop the complete theoretical model, so to say. Still now it is evolving.
স্যার এক্সপেরিমেন্ট গুলো কি করে করা হয়, মানে এটা কি উইন্ড টানেলের ভেতর বা কিছু এরকম টাইপের করে?
Wind tunnel is one means of experiment where you can have the different type of flow situation. I mean, for example, I mean, say here, this typical figure, I mean, this typical video that you can observe is a numerical result. Okay, this is just an animation. Okay, for a fully developed flow. Now, if you want to see some kind of experimental observation, this is a smoke study. I mean, smoke for videography, a very high speed. I mean, so which actually denotes, I mean, you can very clearly observe the wake region. It's a tennis ball, or in other words, it's a sphere. So this is a point of separation, and this
মানে ধোঁয়ার স্ট্রিম ছাড়ে, তাই না?
Smoke is being, I mean, basically from a nozzle, you are having a blower. Okay. So using a blower, you are having an air jet coming out from a nozzle at a constant velocity. So that is your free stream velocity. Now you are injecting smoke in order to get it visualized, right? So that can be photographed. So flow visualization is a very widely applied technique for fluid mechanics experimentation. Okay, so in case of liquid, we use dye, different colored substance are being used. For example, in Ron's experimentation, when you get chance to see, these are some other example actually. What I am looking for is a separation. Yeah, this thing. This is this one. আচ্ছা, তোমরা কি এটা দেখতে পেলে আগেরটা?
দেখতে পাচ্ছি না
স্যার, আপনার স্ক্রিনটা তো
শেয়ার করা আছে।
আচ্ছা, one second. তাহলে স্মোক বললে কি করে? Just a minute.
আমি ভাবলাম মুখে বলছেন হয়তো।
না, দাদা, let me show you this one. এক সেকেন্ড, এটা কি করে করে? Entire screen. Okay. আচ্ছা, আমরা প্রথমে যেটা দেখাচ্ছিলাম, এটা বলছিলাম, এটা একটু ছোট হবে। I don't know whether you are able to see it. So this is the one which actually I was referring to. So you can see the wake region very clearly.
এটা ম্যাক্সিমাইজ করা যাবে না?
না, এর থেকে বড় করা যাবে না। এটা অদ্ভুত, এর থেকে বড় হয় না। Okay. Anyway, I will try to find out the source video, and then I can share with you. So this is what actually I was talking about. That this is the experimentation where the flow is emerging probably from a nozzle supplied to a blower, and then some smoke is being injected in order to get it visualized. Likewise, if it is water, you can also able to see it by injection of dye, some colored substance. So regarding the separation, actually, here, now look into this particular cross section, which is the streamlined body, the schematic, I think already you have seen in the note. Okay. Now here this wake region is this much amount, if you follow the mouse pointer. Now if it is being slightly if the orientation is slightly changed, now you can see the difference. Okay, 5 degree, then 10 degree more. Actually the inclination with respect to the direction of flow is being changed. This is the wake region now, and as you can observe the shift of boundary layer separation point, or the separation point. So initially when it was 0 here, typically you have these two as the separation points, and this is the wake region. As you go on changing this inclination, so more and more typically the upper portion of the body is entirely almost having the wake region, and more this angle of attack or this inclination is changing. It is resulting more and more form drag, right? And if you go on decreasing this, you are actually reducing the form drag, but you are increasing the skin friction drag, because here this surface area is in contact with the fluid. So the first part of our study, that is the valve shear stress, will be, and along with that, this area will be increased, and you are having more amount of skin friction drag, but minimum amount of form drag. So this is what actually I was trying to communicate you, that the trade-off or the optimization is required to get the minimum total drag. Actually, it is the total drag which is of our concern. So this is a kind of an experimentation which are being compiled. Okay, typically you can see these are smoke photography. Okay, so very sophisticated experimentation, but not new, which after compilation and then by some kind of programming, I think, which gives you some kind of user interface, GUI. So which actually these angles I'm changing by clicking this arrow. So it's a beautiful video compilation that gives us idea about how this separation phenomena along with the skin friction drag. Okay, so there are other videos which I think we can try to go through if time permits, but today I think, as I have started with some other agendas are there, so I think I need to stop on boundary layer flow, and whatever is left, yeah, I think that you should go through and let me know if you have any kind of query on that, because we are left with, I mean, today these two are very fundamental one, and some kind of criticalities were there. But after understanding that, I hope you can able to go through the remaining part. The Karman Vortex Street, that video also we will see later. But first I need to have you go through this part and let me know whether you have understood it properly or not. That is the flow pattern in the wake. Its dependence on Reynolds number, which results Karman Vortex Street, and that actually gives you can see a very interesting video which happened in real world, the collapse of Tacoma Bridge, then the separation of boundary and the very cross section, that is the airfoil structure and the airfoil design, that for aerodynamics, and the nature of the variation of this drag force, along with that the lift force, some kind of lift force you have studied in potential flow. Here also you can have the lift force possible by changing the orientation of the body with respect to the direction of flow. And towards the end, we are having control of boundary layer separation. One already you have seen. So these parts are there in the note, and I think in the recorded lecture also. So these I think you should go through first. And
so while you were discussing on the part of separation of boundary layer, is it a necessary condition that dp by dx has to be greater than 0 for a reverse flow? Or there can be any added on forces or contributing factors which can help in reverse flow?
you can have another source on the other side that also may cause flow reversal. But the one where you are having, basically, see, the thing is that here we are having a body which is fixed in space, and as if you are having a flow occurring, flow which is passing over the body. Okay, so that is typically the one which is being done in experiments, in prototype in wind tunnel, where the body is fixed and you are actually supplying fluid at different velocities. But in real situation, say you may be a runner, athlete, okay, or you may be driving a formula car or any kind of a car, or you may be a pilot who is flying an aircraft. Okay, so there you are actually you are generating a speed through a rather stagnant or a static fluid condition. Maybe, may not be, because there could be a wind direction, a wind velocity existing. It may be in the direction of your movement, it may be in the other direction as well. So those are the situations. But always you can have the relative condition. That means basically I'm talking about the coordinate system, how you fix it, depending on that, how you are looking at the problem in a convenient manner. Okay. So if I fix the coordinate system with the body, I can only have a flow direction from left to right, possibly if the body is moving from in the left direction. Okay, so it is basically the resultant velocity that we are looking at. I'm talking about if there is any possibility of other source of velocity apart from the one which we are denoting as u naught, as the free stream velocity. Getting my point? So there could be other direction of velocity. So it is the velocity and the pressure and their interrelationship that we are actually trying to understand in a straightforward manner rather. Because if you add other sources, of course, those would be there definitely. So this is the initiation. There could be other direction of velocity apart from the one which we are continuously considering as parallel. Okay, there could be other. I mean, in a flow direction inclined. So you need to have a component. So complications can always be injected, and in real situation, definitely there are such type of situations. Maybe here we are having only one aerofoil in your screen. You can see this is only one aerofoil. Typically, if you look towards the wing from one side of an aircraft, this is the cross section you can see. Okay, so maybe there could be one body and there could be effect due to another body which is very close to it. Okay, so that will cause a very complicated flow situation. Okay, so there is no end of it. That is what I'm trying to say. It is just the route that I am showing you, that this is the way by which you can start the analysis part or start the understanding. Okay, so is it clear?
Yes, sir.
Okay. Okay, so I mean the second part, I mean we need to move very quickly. What about the second one? That is, what about your problems on potential flow? I think you have done it. All of you have done it. Any problem with this second problem sheet? What is your feedback?
Sir, I have problem in the question number 6. Sir, how to find a Y max? I couldn't find it.
Okay, question number 6. Anything else? The others are true. Only problem 6.
No, sir. The problem is, sir, my the swing function is getting positive, but in the answer sheet it is negative.
Which one?
Sir, problem number 8.
8, you are having the magnitude matching, but the sign is different.
Yes, sir. Magnitude is same, but the sign is different, and the pressure is also different. The answer of pressure.
Magnitude matching, sign problem, sign different, and the pressure is not matching.
No, sir.
Others? What about the others? Problem 8, anybody has done? Okay, 6 and 8. Anything else? Others you have done?
Sir, from 9 to 13, I haven't tried.
You haven't tried. Anybody tried? Anybody else who has tried all the problems? There are total 13 numbers of problems. So you have tried all? Nobody tried. Okay. I need to get the full feedback. Then only I think it will be wise to have a session on doubt clear. Otherwise, we need to have multiple sessions. Okay. So,
Okay, sir.
so that I think this should be done. So then the third point is the class test, because as per the academic calendar, we need to have one class test within this particular window. Typically, I talked with my co-teacher, and we are looking to take this particular class test next week. Typically, next Wednesday, if we fix 3rd. There is 3rd November, 3rd or 4th November, I think. Okay.
So syllabus.
Yeah. If you, I mean, so 4th. First, we need to fix the date and time, and then syllabus, because the mode is online, of course.
Sorry.
হ্যাঁ, কি একটা বলছিলে কেউ?
হ্যাঁ স্যার, জিজ্ঞেস করছিলাম ওটা পেন পেপার মোডে হবে তো নাকি গুগল ফর্ম?
City date তাহলে first of all we are agreeing that it will be on 4th 21, that is Wednesday.
স্যার 4 তারিখ কিন্তু কালী পূজা আছে, মানে ছুটি থাকবে না তো ইউনিভার্সিটি?
Sir, I think the 3rd November is Wednesday. Sir, 4th November is 3rd.
ঠিক বলেছো, 3rd November, yeah, right. Okay, 3rd November, and it will be on pen paper. I mean, to be submitted through Google form probably. That we will intimate you. Okay. So it will be 30 marks. 30 marks. And duration. How much you want?
গুগল ফর্মে হলে তো কম, মানে পেন পেপার না গুগল ফর্মে?
Pen paper.
পেন পেপার তারপরে পিডিএফ আপলোড করতে হবে।
ও মানে করে আপলোড করতে হবে?
হ্যাঁ, pen paper to be.
Sir, the time duration of 3 to 4 hours would be suffice. কেন কি আপলোডিং এর টাইমে একটু অসুবিধা হয়, মানে ওই রিডিউস করতে হয় তো সাইজটা, তো ওইটা একটু টাইম লাগে।
Through G form. Okay. এটা হলো the duration 3 to 4 hours. Good enough for you, all of you.
Yes, sir.
Okay, so let us remind the maximum. There is 4
Yes, sir.
hours.
Okay, sir. Yes, sir. Yes, sir.
4 hours, not more. This is the maximum time duration. So this duration we need to accommodate. So the start time, let us say, this fixed is 10:30. তোমাদের অন্য কোনো ক্লাস হচ্ছে না নাকি? 10:30 কোনো অসুবিধা নেই তো?
তো ওয়েডনেসডে 10:30 স্যার হবে না স্যার।
স্যার আমাদের সেশনাল আছে স্যার A1 এর 11টা থেকে।
ওকে, তাহলে কতটা থেকে করে বলো? You propose.
আমাদের ওয়েডনেসডে তো 3টা থেকে হয়ে যাবে স্যার। বিশাল
না না, সেশনাল আছে।
B2 এর আছে, মেশিন ড্রয়িং আছে।
তাহলে বলো কখন, বিকেলে, সন্ধ্যাবেলা? This is important because you have to satisfy all the subsections. All means total 6 sections should be.
স্যার আমি বলছি কি, আমরা এটা ডিসকাস করে নিয়ে আপনি জানাই, তাহলে ভালো হবে কি?
হ্যাঁ, আজকের মধ্যে ডিসকাস করে জানালে হবে, কোনো অসুবিধা নেই। কিন্তু আমরা যেটা ফিক্স করছি সেটা হচ্ছে মার্কস 30। ওকে, এটাতে কারো কোনো অসুবিধা নেই, আই থিঙ্ক। ডিউরেশন 4 ঘন্টা ম্যাক্সিমাম।
ইয়েস,
ঠিক আছে।
ইয়েস,
this is the maximum duration that includes download, upload, okay, everything. হ্যাঁ, আচ্ছা, এবার হচ্ছে including download and upload and any other thing, any others. Okay, শুধুমাত্র এই দুটো ইউ নিড টু লেট আস নো। ওকে, আমাদের যে হোয়াটসঅ্যাপ গ্রুপে এটা স্টার্ট টাইম আর এন্ড টাইমটা একটুখানি করে দেবে, মানে মধ্যরাত্রির করো না। নেক্সট হচ্ছে সিলেবাস। syllabus. Syllabus হচ্ছে আমরা up to momentum integral equation. Okay. And starting from viscous incompressible flow, potential flow, okay, আর বাউন্ডারি লেয়ার ফ্লো এইটুকু থাকবে, পুরোটা থাকছে না, ঠিক আছে?
তাহলে সলিউশনের আগে পর্যন্ত মানে অ্যাপ্রক্সিমেট সলিউশন আর ল্যামিনার
হ্যাঁ, ওটা ঢুকিয়ে নেবো। অ্যাপ্রক্সিমেট সলিউশনটা রাখা যেতে পারে, অসুবিধা নেই তো। মোমেন্টাম ইন্টিগ্রাল ইকুয়েশন তাহলে এটা অ্যান্ড ইটস অ্যাপ্লিকেশন। হ্যাঁ,
পুরোটাই তার মানে বাউন্ডারি লেয়ার থিওরেম আর পোটেনশিয়াল আর
না, বাউন্ডারি লেয়ার থিওরেম পুরোটা না, অ্যান্ড ইটস অ্যাপ্লিকেশন ফর লামিনার ফ্লো আমি লিখছি। হ্যাঁ,
আচ্ছা,
ওই টার্বুলেন্ট পাইপ ফ্লোর অ্যানালজি ইত্যাদিটা বাদ দিয়ে দিন।
ওকে,
ঠিক আছে, আই থিঙ্ক দ্যাট উড বি কমফোর্টেবল ফর ইউ। ঠিক আছে, তাহলে ভিসকাস ইনকমপ্রেসিবল ফ্লো পুরো থাকছে, থিওরি প্রবলেম, পোটেনশিয়াল ফ্লো পুরোটা থাকছে, ঠিক আছে, আর হচ্ছে এই বাউন্ডারি লেয়ার ফ্লো আমরা আজকে যতটা করেছি তার থেকে একটু কম। আজকে অলরেডি আমরা ডিসকাস করলাম অনেকটাই, বাউন্ডারি লেয়ার ফ্লো সেপারেশনের অনেকটাই করলাম, একটুখানি বাকি আছে, সেটা কালকে হয়তো করে দেওয়া যাবে। তাহলে বাউন্ডারি লেয়ার ফ্লো শেষ হয়ে যাবে। We will be left with this problem discussion on potential flow. সেটা তোমাদের ফিডব্যাক পেলে পরে, কমপ্লিট ফিডব্যাক পেলে আমি ডেট দেবো। আদারওয়াইজ আমরা নেক্সট টুইসডে we will go into this compressible flow আমরা শুরু করে দেবো। ঠিক আছে
স্যার।
মঙ্গলবার নেক্সট ওয়েডনেসডে ক্লাস হবে না, যেহেতু এক্সাম আছে। ঠিক আছে, তোমরা টাইমটা start time, end time to be proposed by CS, all CS, লিখে রাখলাম। সিয়াররা সবাই 6 জন মিলে বসে বাকিদের সাথে কথা টথা বলে আজকালের মধ্যে জানিয়ে দেয়। ঠিক আছে, তাহলে আমরা এটা ফাইনাল করে নেবো। তোমাদের অন্য ক্লাস টেস্ট কি হয়ে গেছে অন্য সাবজেক্টের?
না স্যার।
ঠিক আছে, তাহলে এটা আমাদের একটা হয়ে যাবে, অনলাইনে এটা হবে। তারপর খুললে পরে কি হবে না হবে জানি না, তখন দেখা যাবে। ঠিক আছে, এটা হয়ে থাকলে
স্যার এমনি আপনারা কি কোনো ডেট পেয়েছেন যে কখন কলেজ খুলবে না খুলবে, ওরকম কি আছে ইনফরমেশন আপনার কাছে?
না, তোমাদের কাছে যা আছে আমাদের কাছেও তাই আছে অ্যাজ অফ নাও, যেটা নিউজ মিডিয়াতে যা, নট মোর দ্যান দ্যাট। ঠিক আছে,
ওকে স্যার। আগামীকাল ক্লাস হবে না?
হ্যাঁ, আগামীকাল তো হবে। আমি আগামীকাল বাউন্ডারি লেয়ার ফ্লো যতটুকু বাকি আছে সেটা তাহলে আমরা ডিসকাস করবো।
ইয়েস ওকে,
ঠিক আছে, তাহলে পুরোটা শেষ হয়ে যাবে বাউন্ডারি লেয়ার ফ্লো।
ওকে স্যার।
আর নেক্সট মঙ্গলবার ক্লাস হবে, সেটা হচ্ছে যদি তোমরা পোটেনশিয়াল ফ্লো প্রবলেম নিয়ে ডিসকাশন চাও, নেক্সট মঙ্গলবার করা যেতে পারে, কিন্তু সেটা আমাকে একটু জানিয়ে দিতে হবে 2-3 দিন আগে। আদারওয়াইজ কম্প্রেসিবল ফ্লো আমরা শুরু করব।
ঠিক আছে
স্যার।
কি বলছিলেন?
স্যার বলছি একবার ওই ভিডিওটা দেখাবেন, ওই এরোফয়েলের ওই স্মোক ভিডিওটা, একটা জিনিস দেখতাম।
1 মিনিট। বাউন্ডারি লেয়ার ফ্লো না, আচ্ছা, এটা করি। এটা
হ্যাঁ, এটা বলছি এখানে আমাদের যদি এরোফলটার মধ্যে একটা স্লট থাকে, তাহলে তো এই ফ্লো সেপারেশনটা কিছুটা হলেও নিউট্রালাইজ হবে না?
হবে তো,
মানে
থাকে তো
ধরুন
এরকম।
শেষের দিকটা একটা মানে ফাঁকা জায়গা আছে, যেখান থেকে নিচ থেকে এয়ারটা উপরে যাবে, তো সেটাতে
হুম,
মানে
হুম,
কিছুটা
হুম,
হলেও
হুম,
নিউট্রালাইজ হওয়া উচিত।
সেটা করা হয় তো, এয়ারক্রাফট ডেলিবারেটলি কিছু প্যাসেজ করা থাকে, হ্যাঁ, যাতে করে তোমার ওটাকে রিঅ্যাটাচমেন্ট আবার করা হয়, যাতে করে তোমার এই সেপারেশন পয়েন্টটা ডিলেড হয়, আরো পেছন দিকে চলে যায়, ফলে ড্র্যাগ কমে যাবে, ফর্ম ড্র্যাগ কমে যাবে। সো দিজ আর অ্যাকচুয়ালি ডিফারেন্ট মেথডস অফ কন্ট্রোল অফ বাউন্ডারি লেয়ার ফ্লো সেপারেশন। ওকে, ঠিকই বলেছো। এটা দেখবে আছেও তোমার, আমার নোটটাতে আছে শেষে, যে এরকম এখান থেকে একটা স্লট মতো করা থাকে। অ্যাকচুয়ালি এটা তো আমরা যেটা দেখছি সেটা একটা 2D প্ল্যানার ভিউ, 3 ডাইমেনশনাল, ফলে স্লটটা বিভিন্নভাবে প্যাসেজটা করা থাকে বডির মধ্যে ছোট ছোট, যাতে করে কি হয়, ফ্লোটা এখান থেকে ঢুকে এদিক থেকে আবার ইমার্জ করছে, ফলে যেটা হচ্ছে এই সেপারেশনটা হচ্ছে একটা ফেনোমেনা, তার তলা দিয়ে আবার একটা ফ্লো চলে যাচ্ছে, ফলে সেটা অ্যাটাচ করে নিচ্ছে। তো দ্যাট উইল অ্যাকচুয়ালি রিডিউস দ্য ফর্ম ড্র্যাগ। ঠিক আছে, ঠিকই বলেছো। তো এটা আমরা কালকে বেশ কিছু আরো টুকটাক কয়েকটা ভিডিও দেখলে আরো ব্যাপারটা আমার মনে হয় পরিষ্কার হবে কিছুটা, এবং ভালো লাগবে দেখতে। আই থিঙ্ক এখানে বেশ কিছু আরো কয়েকটা ভিডিও আছে। ঠিক আছে, আর বাকি পার্টটা আমরা ডিসকাস করে নেবো, খুব অল্প পার্টই আছে, বেশিটা নেই। ওকে, আর কিছু আছে জানার?
স্যার বলছি আইডিয়াল ফ্লোতে আমরা দেখছিলাম স্যার, মানে সুপার ইম্পোজ করে দুটো বেসিক ফ্লোকে, সেটা একটা শেপ আসছিল স্যার। মানে ওটা স্যার মানে ফ্লো এর সাথে আমরা শেপকে কেন তুলনা করছি, ওটা স্যার একটু বুঝতে পারছি না।
এইটা বলছো?
হ্যাঁ মানে মানে ধরুন ওই র্যানকাইন ওভালের ক্ষেত্রে মানে আমরা বলছি স্যার ওটা ওভাল হবে, মানে হাফ
হ্যাঁ,
বডির ক্ষেত্রে, র্যানকাইন
হ্যাঁ,
হাফ বডির ক্ষেত্রে। তো স্যার
হ্যাঁ।
ওটা তো মানে অ্যাকচুয়ালি ফ্লো স্যার, মানে ওটাকে আমরা বডি হিসেবে কেন
ওটা অ্যাকচুয়ালি ফ্লো, ওটা অ্যাকচুয়ালি হচ্ছে কিছু ম্যাথমেটিক্যাল ইকুয়েশন। হ্যাঁ, ওটাকে আমরা কেন বডি বলছি, তার কারণ হচ্ছে যে তোমাকে বুঝতে হবে যে স্ট্রিমলাইন পাসিং থ্রু দ্য স্ট্যাগনেশন পয়েন্ট, এইটা হচ্ছে অ্যাকচুয়ালি একটা মানে একটা ডিমার্কেশন বিটুইন টু রেজিম, ওয়ান ইনসাইড দ্যাট পার্টিকুলার স্ট্রিমলাইন অ্যান্ড ওয়ান আউটসাইড। এবার প্রত্যেকটা কম্বিনেশনের ক্ষেত্রে খেয়াল করে দেখবে যে তোমার ওই যে স্ট্রিমলাইনটা আমরা বার করছি এবং সেটার যে প্লটটা যদি করি, তাহলে তার বাইরের ফ্লো এর প্যাটার্নটা একরকম, তার ভেতরের ফ্লো এর প্যাটার্নটা একরকম। এবং ওই স্ট্রিমলাইনটা একটা কোনো বডির কন্ট্যুরকে আমরা বেসিক্যালি আমরা কনসিভ করছি, জিনিসটা অ্যাকচুয়ালি ওটা কোনো বডি নয়, ইট ইজ ফ্লো, অফকোর্স হোয়াট ইউ আর সেইং। ঠিক আছে, কিন্তু যেহেতু it gives two different regime of or two different characteristics of flow, one inside one outside, so ইনসাইডটাকে আমরা যদি ইগনোর করি, অর ইন আদার ওয়ার্ডস আমি যদি ভাবি যে ওটা একটা সলিড বডি, ওরকম যে বডিটা ওপর দিয়ে ফ্লো হলে তার স্ট্রিমলাইন গুলোর প্যাটার্নটা নাকি অনেকটা ওরকমই হবে, বুঝতে পারলাম? সো ইট গিভস ইউ দ্য আইডিয়া অফ আ বডি শেপ। It's a clue actually towards designing a body shape, which subsequently এক্সপেরিমেন্ট করে, ধরো এরকম একটা বডি শেপ তৈরি করে, উইন্ড টানেল এক্সপেরিমেন্ট করে, এইরকম যে স্মোক টানেল এক্সপেরিমেন্ট যেগুলো দেখলে ছবি কয়েকটা, সেরকম যে স্ট্রিমলাইনগুলোর চেহারা যদি দেখা গেছে যে দোজ আর ভেরি ক্লোজ টু দ্য ওয়ান্স প্রেডিক্টেড বাই পোটেনশিয়াল ফ্লো থিওরি। ওকে, যেটা অলরেডি ধরো এই এরোফয়েলের যে ছবিটা, যে ভিডিওটা দেখছিলে, তাতে টিপিক্যালি যে স্ট্রিমলাইন গুলোকে আইডেন্টিফাই করা যাচ্ছে, সেটা অনেকটা ওই রকমই একটা র্যাঙ্কাইন ওভালের ফ্লো পাস্ট, র্যাঙ্কাইন ওভাল আর ফ্লো পাস্ট হাফ বডি, which is extended to infinity, অনেকটা ব্যাপারটা এরকম ধরনেরই দেখতে স্ট্রিমলাইন গুলো, তাই না?
হ্যাঁ স্যার, হ্যাঁ স্যার ওরকম।
ওকে, তো আর যদি কিছু না থাকে তাহলে আমরা আজকের ক্লাসটা শেষ করি। ঠিক আছে?
ওকে
Okay, sir. Thank you, sir.
থ্যাংক ইউ।